All right, so this one's a fun one. Not that they're all fun, but this is applications of radical chemistry. So I'm going to be talking about a variety of things that are kind of occurring around us. And the first thing is oxidation of unsaturated lipids. Okay, so remember unsaturated bonds are basically pi bonds, right? We have a double or a triple bond. And unsaturated lipids are you have your triacylglycerols, right? So I'm going to draw a generic, not a generic one, but just a long chain right here with an unsaturated part of an unsaturated lipid, and that triacylglycerol though I'm just going to write R groups for the rest of them so it doesn't get too crowded. But the point is, let's focus on the double bonds, right? Or this region at least. So, since we really only care about that portion, I want you to focus on these pi bonds, right? Then we can point out the fact that there are three allylic positions in this particular lipid. And if we're talking radical chemistry, right, then that's the site that, or those are the sites that oxidation may occur, or radical chemistry may occur. And so, which is the most readily cleaved would be the question. And hopefully, you can see that that middle one with the triangle around it is the best option because it's in resonance with the pi bonds on either side of it. Okay, so it's got more resonance structures, so it's more stable, which means that hydrogen bond, that CH bond, is going to be a little bit weaker. So we've got I'm gonna this these I guess this lipid right here. It's a super long chain. I don't want to draw the whole thing, so I'm cleaving on either side just to kind of cut it short for you. And let's just focus on this region, right? So we still have all our allylic positions, and what we want to do is look at the oxidation process. So remember, oxygen is a diradical, and so if we're saying it's going to react with the weakest CH bonds, then this is the one we want to do. So, boom, we've got our allylic radical now after the removal of that hydrogen atom. Okay. And we've got this guy right here just chilling on the side. Don't worry about that guy right now. The OOH. And if we had oxygen still present, which we would, for a lipid just kind of sitting on our counter of our kitchen, another oxygen molecule can come along and react with that allylic radical. Once it reacts with the allylic radical, then we've got this species right here, this peroxy radical. Let me write that for you. Peroxy radical. Okay. Now, it's still a radical, right? So this is a very reactive species that can kind of propagate this oxidation process of the lipid, okay? The unsaturated lipid. It can swoop on another hydrogen atom of another fat or lipid and create that allylic radical. Go ahead and draw that. I need to draw both the products, sorry. So this is going to be the hydroperoxy radical. Gotta throw that hydrogen in there. And then we also have our new allylic radical, right? So since we create another radical, this radical is just like the other one above and can continue the cycle, okay? So it's just like that one right there on the right. So since we reformed that radical and this process can kind of propagate, that's basically when your unsaturated lipids or your like olive oil kind of chilling on your kitchen table or counter, that's when that spoils, and that's when your oils, it could be vegetable oil, olive oil, whatever, your unsaturated fats or lipids, and that's when they go bad and taste gross and rancid. And um, they're actually kind of toxic too. So, I mean, whatever though. Like they taste like I mean, it makes sense, right? They taste gross, so your body's like, "Yo, don't eat that." So don't eat that if it's gross. Okay. Um, Moving on to another application, antioxidants, which obviously we know are good for our body. Vitamin E, vitamin C are the ones we like to eat. BHT is butylated hydroxytoluene. That's the one we probably don't like to eat, but it's in our food anyway. They have similar structures, and one of the common themes is a phenol. For this is for a lot of antioxidants in general, and phenols are super cool. Let's say we have a radical forming; it swoops on that hydrogen atom and forms a phenolic radical. So we got that lone electron on the oxygen, and the reason why these are good antioxidants is because they can kind of scavenge for radicals in our body and react with them before they wreak havoc on more important things, right? And so that reactive radical reacts with a phenol in something and it forms a much more stable radical. And this is a much more stable radical because it actually has 5 resonance structures, which I'm drawing right now. And these resonance structures, since there's 5 of them, that means kind of that's synonymous with stability, right? And so that means that this radical is super stable and not very reactive. So it's not going to wreak havoc in our body like that R dot would. Okay, so whatever that may be, and so that's why antioxidants are so important. Believed to like slow down the aging process or whatever, but that's why vitamin E is super helpful because it's well, I'll show you in a second, but that's wait, we need one more resonance structure. Let's go ahead and draw this guy. All right, just didn't want to miss any. So we're going to put that radical back on the oxygen, but we're putting our pi bonds in a different position. So notice these two right here on the left of the ring, and then on the upper part, they're on the right side of the ring. So that gives us our 5 resonance structures, which is equivalent to stability. And we definitely want some stable radicals in our body if they're going to be there so that they don't mess around with our DNA. All right, so what I'm going to do now is draw out some structures for you. All right, so they're going to be kind of long, so I'll try and pick up the pace. This is vitamin E. So we got that OH group, the phenol functional group. This is a fat soluble vitamin, right? So this is actually protecting our cells, or believed to be protecting our cells. And let me go with another one here. This is the BHT, butylated hydroxytoluene. Okay, looks pretty cool. It's actually a food additive, which that's gross to me because it's also in like ethers, because ethers can form hydroperoxides, which are actually really explosive. It's like called auto oxidation. Just in the presence of air over time, they can form it, and it's really dangerous. But that's why they have a specific shelf life. But I don't like the idea of having something in my food as well as in my like ether that I use in the laboratory. It grosses me out. But it's there indeed. All right, this guy's right. This guy is vitamin C. Anybody remember vitamin C, the singer? Maybe 1, 2, 3, 4, 0 of you. Okay, that makes sense. So vitamin C is water soluble. So this guy's actually going to be pretty good for protecting our blood, right? Things in our blood. I like to think that like when you squeeze lime on maybe avocado or apples, it helps prevent oxidation of them or the browning of those, and you might be able to attribute that to the vitamin C in the lime or lemon. The more you know. All right, so this one right here is cool too because I'm not sure if, I don't know. I feel like it's probably always been a thing even before we knew about this. But putting like rosemary in your olive oil or something, not only does it make it taste good, I love rosemary. My dog actually loves to just roll around in rosemary on our walks. But rosemary has a bunch of OHs on there, phenol functional groups. And so this right here, well, not rosemary has that, but rosmarinic acid has that, which is in rosemary. And yeah, so this actually helps preserve your olive oil or your oils, vegetable oils. Pretty neat, huh? Right? I know. I agree. All right, let's finish that. Protects oils. Cool. All right, so this last portion right here, this is just basically just fun, kind of extra, because you know I'm kind of extra. Um, and so there's a couple things here. So there's combustion reactions. So let's say we had butane, we have a little heat, and we have some oxygen, right? That's the perfect combination. We got our fuel or heat or oxidant, and basically that's going to form CO2 and water, right? And it's believed to be a radical mechanism. And so this guy right here and this guy right here are actually really good fire extinguishing sources. This is halon 1211, aka Freon 12B1. This is halon 1301, or aka Freon 13B1. And so, yeah, these are CFCs if you recognize them from a previous video. And so CFCs are actually really good at extinguishing fires, and they are still used to extinguish fires. And that's because they absorb heat to form radicals. Okay. And why would this be important and helpful in extinguishing fires? Well, once you have these radicals, I just told you that the combustion reaction mechanism is believed to be a radical mechanism, and the radicals in that combustion reaction will react with the bromine radical or the carbon radical, and the reaction is quenched or terminated. Told you I'm kind of extra, but it's all good. We're chilling over here. This next one is soup's cool because science. That's why. So it's about acetamine, acetaminophen OD. So overdosing on acetaminophen. What does that do to your body? Why is it bad for you? Why is too much of that thing not good? Drawing this big old thing out of here. Really, all we care about is that thiol there that I've circled. But there's the structure of glutathione. Okay, glutathione is abbreviated GSH. Okay, and that hydrogen, that H is the hydrogen that's bound to the sulfur, right? And that is definitely an easy proton or hydrogen atom to remove, and a radical reacts with that in our body to make the GS dot, and then that GS dot can react with another GS to form this diglutathione, and that can be reduced to form two regular glutathiones. Okay, and then those glutathiones can now scavenge radicals in our body, because radicals do occur as a result of the like gazillion quadrillion Google amount of chemical reactions that are occurring in our body every day. And so that's the basically the purpose of glutathione in our liver. And so if we consume acetaminophen actually it's processed, or we'll just say processed, using glutathione. And so if glutathione isn't present to do its job of kind of quenching radicals, then those radicals are living longer and able to wreak havoc on our body. And so a normal dose of acetaminophen isn't harmful because your liver is going to be constantly producing glutathione. But if you consume too much or you overdose, then your acetaminophen, the amount of acetaminophen in your body will just essentially consume all the glutathione in your liver. And so this temporary depletion of glutathione allows those radicals to just wreak havoc and cause a substantial amount of liver damage if left untreated, or kind of not if you don't take proper action. And so this could obviously lead to death as well. So that's how bad this basically radical reaction is going to it can be. And so basically the way to kind of fight this is cysteine. So I don't think the doctors give you cysteine exactly. I think it's like a derivative of cysteine, but cysteine is one of the amino acids that has that thiol functional group on there. And so, but yeah, pretty much cool stuff, huh? Science. Bye.